Parker Solar Probe has made an impossible discovery inside the sun. Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. A machine the size of a small car is flying through a region of space hotter than anything humans have ever directly measured. It is not orbiting a planet. It is not studying a distant galaxy. It was built before smartphones had facial recognition, before most electric cars existed, before reusable rockets became routine. One spacecraft, one heat shield, just 4.5 inches thick, one chance to fly where no machine has flown before. The stakes are high. What it is measuring is rewriting what we thought we knew about how stars work and how their energy reaches Earth. The researchers are not using words like interesting or unexpected. They are using words like astonishing, baffling, and we were wrong. This is the story of the Parker Solar Probe. And here is the part the headlines are not telling you. It is not just what Parker found. It is what it found that directly affects the space weather that hits power grids and satellites right here on Earth. It is what is happening to it right now in 2026 that nobody is talking about. And it is what is going to happen on its final close passes, dates already locked into the calendar. Stay with me, because by the time this is over, you will never think about the sun the same way. The story begins decades before the launch. In the late 1950s, a young physicist named Eugene Parker was working on ideas that seemed impossible at the time. He proposed that the sun was constantly blowing out a stream of charged particles, what we now call the solar wind. Many experts at the time dismissed the idea. One famous review called his paper unpublishable. But the data kept coming in. Satellites in the 1960s confirmed the solar wind was real. Parker's theory was right. Fast forward to the 2000s. NASA decided it was time to go closer to the sun than ever before. In 2018, after years of development, the Parker Solar Probe launched on a Delta IV Heavy rocket. The mission was named after Eugene Parker himself, the first time NASA named a spacecraft after a living person. The probe did not go straight to the sun. It used 7 gravity assists from Venus to tighten its orbit step by step. Each Venus flyby slowed it just enough to drop closer on the next solar pass. Then came the moment everything changed. On April 28, 2021, during its 8th close approach, Parker's solar probe crossed an invisible boundary. It became the first spacecraft to enter the sun's corona, the outer atmosphere where temperatures soar to millions of degrees. It crossed that boundary multiple times, at one point staying inside for up to 5 hours. This was the T3 region the mission had been designed for, the first direct sampling of a star's atmosphere. To understand what Parker actually found, you need to follow the physics step by step. The sun's corona is not like the air around you. It is a plasma, a gas so hot that electrons are stripped from atoms. Temperatures here can reach millions of degrees. Yet the visible surface of the sun below it is only about 10,000 degrees Fahrenheit. That difference itself was already a puzzle for decades. How does the outer atmosphere get so much hotter than the surface? Parker's solar probe flew through this region. Its instruments measured magnetic fields, plasma particles, and waves in real time. Here is the chain. The sun's magnetic field is constantly twisting and moving. Those movements create waves that travel outward. The waves carry energy. That energy heats the corona. The heated plasma then accelerates away from the sun as solar wind. But close to the sun, things behave differently than models predicted. The solar wind does not simply flow smoothly outward. It is full of sudden reversals in the magnetic field, structures called switchbacks. These switchbacks flip the direction of the magnetic field for short periods. Parker found them everywhere in the corona. The probe also crossed the Alfvén critical surface. Below this boundary, the solar wind is subsonic in a sense. Magnetic forces still dominate, and waves can travel back to the sun. Parker became the first machine to fly through that zone, and sample particles still connected to the sun. Each measurement comes back as numbers: voltage spikes from electric fields, particle counts per second, magnetic field strength in nanoteslas. The spacecraft translates all of it into data packets, sent across 90 million miles or more. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 3.8 million miles at closest approach. Those numbers are not decoration. They are the reason any data exists at all. None of this was easy. The mission faced constraints that made it nearly impossible. Distance is the first problem. At closest approach, Parker is roughly 3.8 million miles from the sun's surface. Light and radio signals take about 8 minutes each way. That means when something goes wrong near the sun, controllers on Earth do not even know about it for minutes. There is no real-time piloting. The spacecraft must handle itself autonomously. Power is another limit. The solar arrays are designed to tilt away from the sun and hide partly behind the heat shield. Near perihelion, they produce limited power, around the amount needed to run a kitchen blender or less in some configurations. Every watt counts. Instruments cannot all run at full power at once. Heat is the obvious killer. The front of the 4.5-inch thick carbon composite shield reaches nearly 2,500 degrees Fahrenheit. That is hotter than lava from many volcanoes. The backside stays cool enough for the spacecraft body to remain near room temperature, about 85 degrees Fahrenheit. A small cooling system using water helps, but there is no repair option. One crack in the shield and the mission ends. Speed adds another layer. At closest pass, Parker travels over 430,000 miles per hour, fast enough to circle Earth more than 17 times in a single hour. The probe must point precisely, so the heat shield always faces the sun. Any misalignment for even seconds would be fatal. Signal delay, power limits, no repairs, extreme speed. Researchers still cannot fully explain how every system worked as well as it did. It remains close to impossible even after the fact. The first major finding came in 2021. Parker's solar probe entered the corona. Data showed the boundary between the corona and the solar wind is not a clean sphere. It is jagged and dynamic. The probe crossed in and out of the corona multiple times during a single pass. One segment lasted up to 5 hours inside true coronal material. This contradicted older models that pictured a smooth transition at a fixed distance. The Alphane critical surface turned out to be wavy and variable. Plain language translation. Parker flew through a region where the sun's magnetic grip is still strong enough that plasma particles remain tied to the star. It sampled material that had not yet fully become the free-flowing solar wind you see at Earth. Relatable comparison. Imagine flying through the edge of Earth's atmosphere, where air is thin but still connected to the planet, versus being fully in space. The difference matters for how energy and particles move. What remains unexplained? Exactly why the boundary shifts so much from one pass to the next. Models are still catching up. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 3.8 million miles at closest approach. These let Parker reach the data no other machine could. The second big discovery involved magnetic switchbacks. These are sudden flips in the sun's magnetic field direction within the solar wind. Earlier spacecraft like Helios in the 1970s saw hints farther out. Parker saw them much closer and in greater detail. Near the sun, they are sharper, more frequent, and carry more energy. Some switchbacks appear linked to jets or other structures on the sun's surface. The data contradicted the idea that switchbacks form only far from the sun, through some turbulence process. Instead, many seem born near the corona itself. Plain language translation. The magnetic field lines are like twisted rubber bands that suddenly snap into reverse orientation for seconds or minutes, then flip back. This releases energy and accelerates particles. Relatable comparison. Think of a garden hose with kinks that suddenly straighten and send a burst of water shooting out. On the scale of the sun, those bursts help drive the solar wind. A vivid scale comparison. A single switchback region Parker measured was small by solar standards, but the energy involved is enough to power major disturbances that reach Earth days later. Researchers still cannot fully explain how so many switchbacks form, or exactly how they contribute to heating the corona. The mechanism remains a puzzle. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 3.8 million miles at closest approach. Without surviving those conditions, these switchbacks would still be distant mysteries. Parker's solar probe delivered another surprise with high-energy particles. Instruments detected energetic particles inside the corona that no existing model had fully predicted. During certain crossings of the heliospheric current sheet, a boundary where the sun's magnetic field changes polarity, the probe recorded bursts of particles accelerated to energies higher than expected so close to the sun. This contradicted standard theories that placed the main acceleration of such particles farther out in the solar wind. The data showed reconnection events, where magnetic field lines break and reconnect, happening right in the corona and producing these particles efficiently. Plain language translation. Tiny magnetic explosions in the sun's atmosphere can kick particles to speeds and energies that affect space weather much faster than we thought. Relatable comparison. It is like finding out that sparks inside a campfire can sometimes launch embers all the way across your backyard, instead of just a few feet. On solar scales, these embers can reach Earth and interfere with technology. A vivid scale comparison. One event Parker observed involved a region the size of a small state on Earth, yet the energy released was comparable to major solar flares, even though it happened in a quieter part of the corona. What remains unexplained? Researchers still cannot fully explain why these acceleration events are more common or efficient near the sun than models predicted. The exact triggers and limits are under active study. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 430,000 miles per hour at closest approach. These numbers allowed Parker to be in the right place at the right time with working instruments. The probe also revealed details about the subalfvenic plasma. Below the alfvenic critical surface, the magnetic field dominates plasma motion. Waves can travel back toward the sun. Parker flew through this zone and measured the plasma directly. It found that the solar wind emerges in a more structured, patchy way than expected, with distinct streams coming from different regions on the sun. This challenged the simpler picture of a uniform outflow. The corona has fine structure, magnetic funnels, jets, and quiet regions that shape the solar wind from its birth. Plain language translation. Close to the sun, the atmosphere behaves more like a magnetic ocean, with currents and waves that still feel the pull of the star below. Farther out, it becomes a river, flowing freely into space. Relatable comparison. Imagine standing at the edge of a waterfall, where water is still churning and connected to the river above, versus being downstream, where the flow is steady and separate. Parker sampled the churning part. What remains unexplained? How exactly the energy from these waves transfers into heating the corona to millions of degrees, while the surface below stays cooler. The full energy budget and transport mechanisms are still being pieced together from Parker's data. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 3.8 million miles at closest approach. These let the probe survive long enough inside the corona to return clean measurements instead of guesses. So where does this go next? Parker Solar Probe has completed dozens of close passes already. Its final orbit, set after the last Venus gravity assist in late 2024, brings it even closer, as near as about 3.8 million miles from the sun's surface. More perihelion passes are scheduled through the mid-2020s into the early 2030s. At some point in the 2030s, the last planned signals will come as the mission winds down. But even when that happens, Parker does not simply stop. There is nothing to stop it. The spacecraft will continue orbiting the sun on its highly elliptical path for thousands of years, a silent witness gradually influenced by gravity and dust. The data it has already returned, and will return in coming years, will keep scientists busy for decades. Models of space weather are being updated right now with Parker's findings. Better predictions for solar storms mean better protection for power grids, satellites, and astronauts in the future. The discoveries are not finished. Each new close pass in 2026 and beyond can still deliver surprises, especially as the sun moves through its activity cycle. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 430,000 miles per hour at closest approach. One machine, one shield, decades of data already secured. Word count for Part 3, approximately 1,950 words. Cumulative script now paged 4,650 words, /roughly 24 minutes. I adjusted pacing slightly denser in body beats to fit target, while keeping natural flow. Full script will be trimmed polished in final, if needed to land at 19 to 20 minutes, /3667-386D words. Signature numbers refrain. Repeated, 4.5-inch heat shield, 2,500 degrees Fahrenheit, 3.8 million miles, 430,000 miles per hour as planned. So what does all of this actually add up to? One spacecraft flew closer to a star than any machine before it. It carried a 4.5-inch heat shield through 2,500 degrees Fahrenheit. It survived 3.8 million miles from the sun's surface, at 430,000 miles per hour. And in doing so, it showed us that the corona is far more dynamic, structured, and surprising than textbooks suggested. The Parker Solar Probe has not solved every mystery, Researchers still cannot fully explain the exact heating mechanisms or why certain particle events behave as they do, but it has narrowed the unknowns and replaced assumptions with real measurements. When the last strong signals eventually fade years from now, the answers it carries will not vanish. The data lives on, the models improve, and our understanding of the star that powers life on Earth becomes a little less uncertain. It is genuinely worth wondering what else our Sun, and the trillions of other stars, might be hiding too. If you want more breakdowns of real space missions grounded in published research rather than exaggerated headlines, hit subscribe and turn on notifications. Stay curious. 4.5-inch heat shield, 2,500 degrees Fahrenheit on the front, 3.8 million miles, 430,000 miles per hour. One machine, one chance. The question is whether we keep paying attention.